Hey everyone, in this video let's take a look at question 503, next greater element 2 on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question we're basically given a circular array nums, which means that the last element, next element is equal to the first element, so it's basically like linked in a circle, and we want to return the next greater element for every element in nums. So let's take a look at how we do this, and we've done a question similar to this called next greater element 1, and essentially in that one we have the same constraints here, except that in next greater element 1, the array is not circular. So for example, for something like this, 1, 2, and 1, the next greater element of 1 is 2. For 2, it's minus 1. And for 1, it's actually minus 1 again, because we can't loop back to the front and get 2 again. So in this question, we can actually get that, but in original 1, we cannot. In the second one here, you can see that like 1, 2, 3, 2, 3, 4. So I will not go through this one. This one's pretty easy to see. For 4, even if we loop back, we will not arrive at a higher element, so that's why it's minus 1. But for the 3 here, and maybe there was like a 2 here as well, for 3 here, we would arrive at 4, and for this 2 here, we would arrive at 3. So that's what we would do. So how might we go about doing this question? Well, we've already done next greater element 1, and it turns out that we can actually reuse much of the code in that one. So go ahead and watch the next greater element 1 video, but if not, I can go ahead and quickly do next greater element 1 in this problem because we want to use the same code anyways. So let's take a look at how we can do next greater element 1, and I'll go through a little bit quickly in this one because I've already done a video of it in the past. But what did we do in next greater element 1? Well, first of all, we've realized that for these types of questions, when we want to find the next greater or the next smaller, or basically anything in which we have to find an order, right? Like there's something, an order when you're trying to find some sort of element, maybe the next element, smallest distance, or something like that, right? In those cases, we want to use a monotonic stack. A monotonic stack is a stack in which it maintains monoticity, which means it's strictly increasing or it's strictly decreasing. So in the case for next greater element, we used a strictly decreasing monotonic stack. So let's take a look at how we did that, and I'll explain the code as I do it. So first thing we did is we defined our stack, and then we didn't do this in the original problem, but I'm doing it in this one. Essentially, now I'm going to just define my result, and then initially I would just set it equal to minus 1 here, and let me set n is equal to length of nums here. So we have a reference to that, and so this will be like this, and then we'll just return res in the very end. And so in our loop here, when we loop through the actual numbers, so 0 to length of the nums, we will eventually update this res, and so we can return it in the very end. Okay, so what did we do? Well, when we are looping through the numbers, we assume we have a stack, we have decreasing stack, check to see if nums at I breaks monoticity. So we want to basically see if nums at I is breaking the decreasing stack. What does that mean? Well, it means that if my stack is decreasing, it means it has like elements like maybe like 7, 6, and 5, for example, and then I want to add in a number 9 here. Well, obviously this would decrease, this will break the monoticity, right? So in that case, we have to pop off the elements that correspond to this element breaking the monoticity. So in this case, we would actually pop off all of them, but maybe if there was something like a 10 here, we would only pop off these 3 over here. But anyways, what did we do? So we did a while stack, so while stack exists, and stack at minus 1. Now, again, a difference in the main problem. In the original one, stack at minus 1 referred to an actual value, like an actual, like maybe like 1 or like 4, like 2 or like 4 or like 3. But often it's good in these types of questions to not append the value, but to append the index. Because from the index, you always have access to the value, but not the other way around. So in this question, we actually need to append the index. And often for these questions, always append the index. So there's a mistake I made in my first one where I didn't, but always append the index. So if you append the index, then stack at minus 1 is the index. So nums at stack at minus 1 is actually the element. So what I want to check is if this element here, if this is somehow less than nums at I, well, what this means is that nums at I is breaking my monoticity. So what did I do? Well, we popped this last element, and we continued to pop until this condition was false. And then what we did is res at index is equal to nums at I. And so what does this essentially mean? Well, this essentially means the following. Let's just assume that I'm adding in the values here just for clarification's sake, like just to make it easier. But actually, I'm adding in the indices. But let's just make it easier and assume I'm adding in the values. Okay. So what does that mean? Maybe we have like 9, 7, 6, and now I want to add in the value 10. Okay, so what does this mean? Well, if I want to add in the value 10, then for every element that's smaller than it, you can basically understand that the next greater element, it has to be this 10, right? It has to be the element that is breaking the stack. So 5's next greater element is 10. 7's next greater element also 10. 9 is also 10. Maybe we had like 11 over here. 11's next greater element wouldn't be 10 because we wouldn't be popping out 11. But basically, after all of this is done, then our stack would just contain 11 and 10. And so that's what I'm doing here. Res at index. That's why I defined res, so we can refer to res at index is equal to nums at I is equal to the next greater element. Now, if this is not the case, then we just went ahead and we appended the current item to the stack because we understood that this one is not breaking the monoticity. So we did that. And so this solution here would actually work for like a strictly increasing array. So something like 1, 2, 3, it would work exactly. So let's go ahead and do that. Okay, so it works. So now let's see how we can maybe try, move this solution to work with our solution of a circular array. So let's see how we can do that. For a circular array, if you really think about it, like what are we doing, right? So let's say we had the array like 1, 2, 1, right? If we had the array 1, 2, 1, and I said it's circular, what this kind of means is like 1, 2, 1, and then this one goes back to this one, right? So you can kind of think of it as like we just have the same array again, 1, 2, 1. We just have the same array again. So instead of nums, we have like nums times 2, a copy of nums appended to nums itself. And so in this case, it actually becomes very easy to figure out the next element, right? Because initially, like res is -1, -1, -1. But here you can see that for 1, the element is 2. For 2, even though we loop this entire thing, it's going to be -1. But for 1 here, the next greater element must be this 2 here. And so if you think about it in terms of that, we can actually find the solution to this by just duplicating nums. So let's see how we can maybe go about doing that. Well, in that case, what we need to do is, after we've defined the size of our nums, we can go ahead and we can just do something like nums is equal to nums times 2. Now, I don't actually want n to change because I'm going to be using n, and I want n to be the existing value. So let's see what we can do here. Well, I'm going to be still going through all of this, right? So if you think about it, I need to not go through length of nums, but I need to go through length of nums times 2, which is also kind of n times 2 in this case, right? So I can go through n times 2. Right? So I'm going through this entire array here. And now what do I want? Well, I still want res to be size n. So this is still size n. This is size n times 2. Now what do I want? Well, if I'm going through the array, notice that for I can append like I to the stack. If I append I to the stack, the only problem here is that this index that I pop off, I don't ever want this index to be greater than size n, right? Because result is only of size n. I can't pop off like this index, which is index 4, 0, 1, 2, 3, 4, and then do something like result at 4 is equal to whatever. Because result only has a size of 3. It only has a size of n. So what can we do? Well, the only thing we need to change here is instead of stack.append I, we will only append it if I is less than n. We will only append it if I is less than n. And so if we do this, then this essentially doesn't have to change, and actually nothing else has to change. So we can go ahead and we can run our code. And we can go ahead and submit it, and we can see that this is a working solution. Now, why does this work? Well, if you think about it, like what's happening here, even though we are not appending these values, right? Even though we are not appending index 0, we can append index 0, 1, and 2, but we're not appending 3, 4, and 5. Even though we're not appending this, notice that we're still looking at it, right? So if I was to kind of look at my stack, what would my stack look like? Now, here I'm just going to, again, just use the elements just to kind of make it easier. But in the start, I have the element 1, right? And then I pop it off because this 2 is over here. So what I understand is 1's next element is 2. And now I have 2. And then again, I have 1, right? So it's 2 and 1 here. And again, I'm just adding on the elements here just to kind of show you. But in reality, you would add on just the indices. Now, I'm still going to look through 3, 4, and 5, but I'm not going to add it onto my stack. So for this 3 over here, if I add on this 1, well, technically, like it's breaking this monoticity if you think about it, right? Because 1 is, actually, no, it's not breaking it, right? Because 1 is equal. So length, this is actually false, so it won't break it. But if we keep going, so let's say we had this 2 over here. In this case, what happens? Well, in this case, nums at stack at -1 is actually less than nums at stack at I, which means that 1 here is less than the 2. So since this is the case, we would go ahead and we would basically pop off this 1 over here, right? We'd pop off this 1, which corresponds to this index over here, this index 2 over here, and we'd set the next value of that, the next greater element to be whatever we just had, which was the 2 here. And so that's why we have the 2 in the end. And so then we can actually go one more, and then we can take a look at this index 5. And so we can add on this number 1 here. But at the very end, the stack, even though it contains elements, we have already processed everything because we are n times 2. We've already processed everything. And so we can return our result. So this is one way in which we tackle these circular array type problems. You just duplicate the array, and you make sure you don't append to the stack unless you really have to. So we will have this information here. And actually, for all of these, these actually shouldn't even be appended to the stack. But you can notice that we will still have like this nums at I, right? So for the items that are still left on the stack, so we will still have, for example, item 1, item 2, all of this gets taken care of, 2 and then 1. So this 1 doesn't get taken care of, but this 1 gets taken care of over here. So nums at I, when it equals this number 2 here, when I is equal to 4, then we can go ahead and replace this index here with the value. So not this index here, but this will actually be like the value here. So we'll replace it with the number 2. So that's again how that works. So you can think about it like in terms of that solution. Just go ahead and draw out like one example to see why it works. Now, there is actually a way to improve this in that we don't need to duplicate the array. Now, how can we do that? Well, why are we duplicating the array, right? We're duplicating the array because I need to refer to the same element again, right? 0, 1, 2. I essentially need like 0, 1, 2 here again, if you kind of think about it. I need 0, 1, 2 again here. But instead of that, we are having three more indices, but they have the same values here. So what can we do instead, right? What can we do instead? Well, if you think about this one, instead of duplicating nums, why don't we, instead of adding I, what can we add so that we will always remain at 0, 1, 2, right? Like, so instead of like 0, 1, 2 and then just skipping these indices here, maybe I can just repeatedly add in 0, 1, 2. How can I do this one? If I did this one, it would basically be the same, right? I'm just adding in the same element again. So how can I take this approach? Well, you might know this trick or you might not know this trick, but essentially what you could do is instead of adding I, you could actually add on I mod n. So if you do I mod n, n here is the length of the nums. So 0 mod 3 is 0, 1 mod 3 is 1, 2 mod 3 is 2, 3 mod 3 goes back to 0, and then the cycle repeats. So in this case, we will keep on adding 0, 1, 2, 0, 1, 2, etc. And we will still loop from 0 to n times 2, right? Because we still want to loop kind of twice to go through the array. So the kind of changes we have to make here is we'll append on I mod n. And so here, what do we have to do? Well, here, when I'm referring to nums at I here, nums at I can still be like 5, right? But really 5 is referring to 5 mod 3, which would be index 2. So I need to do mod n here. And same thing here, I need to do I mod n here. And then basically that's all I need to do. I can remove this call here because now I can add to my stack since it's just the indices 0, 1, and 2. And so now if I went ahead and I ran this code, you can see that we arrive at the answer. So now if we go ahead and submit it, we can see that it works. So notice that we are still looping only twice, right? So if we were to loop 3 times, then it's possible our solution would like change. But because we are only looping twice, we're guaranteed to just look at the array once. So this 1, 2, 1 once, and then we look at it one more time. And so if we take this approach where we do n times 2, so we loop twice, but we add in I mod n, so then we can actually go back to the front and then just add in the same indices again. And so this is another way in which you can actually solve the same problem. So time-wise, it's just O of n. So O of n times 2 technically, but O of n. And then stack is also O of n. So that's this question.